Swayam Prabha. Digital India. Educated India.
Today we are going to continue our discussions on beam models that we had started in the last class. So, in the last lecture we had looked at two beam models under the assumption that the shear strain in the beam is negligible, or in other words that the beam is infinitely stiff in shear. Now, this assumption is very good if the beam is slender, which means that its transverse dimensions are much smaller than the length of the beam. So, under such assumptions, such an assumption, this shear may be neglected, so that the Euler-Bernoulli hypothesis, in which says that the plane sections perpendicular to the neutral fibers before deformation also remain plane and perpendicular to the neutral fibers after deformation. However, when the beam becomes thick, or its slenderness ratio it goes on reducing, so it becomes more and more thick in the transverse direction than in the length direction. In that case, shear becomes important. So, today we are going to look at a model which incorporates this shear in a very interesting manner. So, in the previous lecture what we saw, that the shear force was introduced in the equilibrium equations. It was not a quantity derived from the deformation of the beam in terms of the material properties. But today we are going to look at this more advanced beam model, which goes by the name of Timoshenko beam model. So, we are going to look into this modeling of the Timoshenko beam. So, the assumptions that we made in our previous lecture, that the slopes are small, the material is linearly elastic, homogeneous and isotropic, all those assumptions still hold, except that now we are going to introduce shear in our model. So, let us look at this Timoshenko beam model. Here I have introduced what is the basic difference between the model that we discussed in the previous lecture and what we are going to discuss today. So, here you can see an undeformed element of the beam which undergoes flexure or pure bending. So, this is what we discussed in our last lecture. So, this is the neutral fiber or the neutral axis, and the cross section of the cross section maintains this orthogonality with the neutral fibers. So, this is known as pure bending. Now, in this case the slope is nothing but this angle psi that I have indicated. So, when a beam undergoes pure bending, then the slope of the neutral fiber, we remember that we are always tracking the slope of the neutral or the deflection and the slope of the neutral fiber. So, this slope is this angle. Now, let us look at this case of simple shear, when the element undergoes a simple shear. So, here this is this simple shear is a volume preserving deformation. So, this angle theta is the shear strain, this is the angle, that is the shear strain. And as you can see here, that the slope of the neutral fibers or the neutral axis is nothing but this shear strain. So, therefore, when we put these two things together, which means that a beam undergoes both flexure and shear. So, it is under it is under bending and shear. So, the total picture looks like this. So, this is the pure bending picture, this is the simple shear picture, and the net result is shown here. Now, you can see that this shear, because of the shear, the angle does not change, as you can see here. So, this was vertical, so this remains vertical. So, which means that this angle will not change, the angle measured from the vertical, this angle remains psi, whereas the slope of the neutral axis changes, and this is what we have. So, the net slope of the neutral axis del w del x is the angle because of pure bending and the shear strain. So, that is the total angle. So, we are representing the slope of the neutral fiber in terms of this flexure angle and the shear strain. So, we can consider our field variables when we denote or represent the deflection of the beam. We can use any two of them. So, what we will do is we will choose w and psi as our field variables. So, this is the transverse deflection and this is the flexure angle. So, these are the two field variables that we will use. Now, let us then start representing our deformation in terms of these field variables. So, the first thing is the strain. So, the fiber strain transverse to the in the longitudinal direction of the beam. So, if you once again consider fibers at a height z from the neutral plane or the neutral axis, then following our discussions in the previous lecture, we can write the length of this fiber. So, if rho is the radius of curvature, then rho minus z, which is this radius, times, so this angle is d psi. So, the additional angle so, we are considering an element between x and x plus dx. So, so the strain can be written as the length of the current length of this fiber minus its initial length divided by, so that is the length of the element. So, this can be written as minus z del psi del x. So, this is in terms of the angle by which this section has rotated. So, that is the strain in this fiber. So, if z is positive and del psi del x is positive, then you can see that this strain is compressive. Then we can write stress using Hooke's law. So, that then becomes, so here now with this expression of stress, we follow the steps that we carried out in our last lecture. We determined the bending moment, negative of sigma times dA, this is the force. So, on cross, so z cross the force, so that integrated over the area, and then if you substitute this expression of sigma, then you can easily see the way we have done before. So, the bending moment turns out to be E I del psi del x. Now, the next thing is to determine the shear force. Now, in the models that we looked at in the previous lecture, shear force was introduced in the equilibrium equations, considering that the beam element is infinitely stiff in shear. But today, since we have introduced the shear strain, so we know that the shear strain given by theta is nothing but del w del x minus psi. So, we can represent shear strain in terms of our field variables w and psi. Then I can write the shear stress acting on so the shear stress is G times the shear strain, where this is the rigidity modulus times the area of the cross section, that is going to give us the total shear stress. Now, as you know that in a beam, what we learn in mechanics, that the shear stress is not uniformly distributed over the cross section. So, just multiplying it with the total area of cross section is actually going to estimate the shear stress. So, the shear stress will be actually lower than just a product of the shear force will be less than just a product of the shear stress and the area of cross section. So, what we do to remedy this problem and to keep the formulation very simple, we introduce what is known as a shear correction factor. We calculate a corrected area where AS is the actual area of cross section of the beam divided by a factor kappa, where kappa is known as the shear correction factor. So, as you know that say for example, in the case of a rectangular a beam with a rectangular cross section, the shear stress distribution is parabolic. So, it is parabolic, it is maximum at the neutral fiber and reduces and goes to 0 at the top and bottom fibers, because there is no shear stress on the top surface and the bottom surface. So, the distribution of shear stress in a rectangular beam with rectangular cross section is parabolic. Now, to take care of this fact, we introduce the shear correction factor and calculate a reduced area and multiply this area with the shear stress to determine shear force. So, we want to keep the expression of this shear force simple. So, for that reason we have introduced this shear correction factor. Now, this shear correction factor typically these take on values of about 1.2 for rectangular cross section, it's approximately 1.11 for circular cross section, and it is from about 2 to 2.4 for beams with I cross section, I beams. So, these are some typical values that are used in various situations. Now, here we now have a very simple expression of the shear force acting on the cross section. So, therefore, we can write this as so that is the expression of our shear force. Now, so we have these forces and moments let us look at the free body diagram of this beam element. So, this is an exaggerated view. So, this is the transverse deflection at x at time t. Here we also have these shear force and the bending moment. So, if you write down the transverse dynamics for this element, so if rho is the density of this material, A is the area of cross section, then rho times A is the mass per unit length times dx, which is the length of this element, is the mass of this little element multiplied by the acceleration, and that must be equal to. So, here again considering that the slopes are small, we can write this as the forces in the transverse direction. So, V plus dV cosine of this angle, so that is approximately 1 minus V times cosine of this angle, which is also very small. So, this is what we have. So, dividing throughout by dx, now we know that this expression of V. So, we have this expression of V. So, introducing this expression here, so this is our equation of transverse dynamics for this element. Now, the next thing is the rotational dynamics. So, rho times the second moment of area about the neutral axis. So, this, as we have discussed previously as well, this is the moment of inertia about the neutral axis per unit length. So, this times the length of the element would give us the moment of inertia about the neutral axis, which is perpendicular to the plane of the paper. So, this times the angular acceleration. Now, this angle is the rotational angle is psi. So, this is the angular acceleration, and that must be equal to all the moments about the so this gives us so this on the right hand side we must write all the moments about the center of mass of this element. So, we have because of this shear force, and because of the moments, bending moment. So, we obtain dividing over by dx and considering that dv dx is of smaller order, then we obtain the equation of motion Now, once again substituting these expressions of shear force and the bending moment in here, the bending moment is E times I times del psi del x, and this is what we obtain as the equation of motion of the rotational dynamics. So, these two equations now you see we have two field variables w and psi. So, we need two equations of motion. So, these are the two equations of motion in w and psi. Now, they are coupled partial differential equations. Now, for so here in general this area of cross section can be a function of x. So, similarly, this moment of inertia can be a function of the second moment of the area can be a function of x for a beam with varying cross section. For a beam of uniform cross section, these equations will of course simplify. So, this is the equation of motion of the transverse dynamics. So, this is for a uniform Timoshenko beam. Now, here it is possible to eliminate psi between these two equations to obtain a single equation in W, and to do that so here if you differentiate this equation with respect to x, so you will have del psi del x in all these in this equation, and del psi del x can be solved from here. So, from here I can write and differentiating this equation with respect to x, now we are going to substitute or eliminate del psi del x in this equation using this expression. So, if you do that and simplify, so this is what you are going to get. Now, this equation is in terms of this field variable w, but then notice that here you have fourth derivative with respect to time. This has fourth derivative with respect to the space. So, to solve this equation, you need to have 3 initial conditions and boundary conditions, the number of so you will need 4 initial conditions and 4 boundary conditions. So, and that you usually do not have, I mean 4 initial conditions you definitely do not have. The reason is that, so the reason that this equation, though this is correct, but when you solve this requires a little care, because this is going to generate 4 constants of integration for the time integration and 4 constants of integration for the spatial integration. Now, to solve for these 8 unknowns which you actually do not have. So, what you will have to do is the general solution of this has to be once again substituted in these equations to find out additional constraints. So, when you solve if you want to solve this, then you have to be little careful, you have to do some additional steps. Usually this is used to determine what we discussed in one of our previous lectures, and what we are going to also discuss. This is used to determine the dispersion relation for the Timoshenko beam. So, that is the equation of motion. Now, as we have discussed previously, we also would like to have a variational approach for deriving the equation of motion of a Timoshenko beam. The reason being, this gives us our boundary conditions directly, which we have not discussed as yet. So, we will look at the boundary conditions from the variational principle, and also I mean the variational principle gives us a very powerful way of approximately solving these systems, as we have seen before. So, let us look at the variational formulation of for the Timoshenko beam. So, in the variational formulation, we write down the kinetic and potential energy expressions. So, the kinetic energy is 1/2 mass per unit length times the velocity square. So, this is the translational kinetic energy plus 1/2 rho times I is the moment of inertia per unit length times the angular velocity square. Now, this is per unit length, this is kinetic energy per unit length. So, multiplied by a small length of the beam and integrating over the length of the beam will give us the total kinetic energy of the beam. Now, the potential energy. So, here I am using the same symbol V for potential energy. So, that is given by 1/2 E I the second derivative of W with respect to x square this. So, this is the potential energy due to flexure. So, this we have written in terms of psi, a single derivative. So, psi single derivative, and that is the expression that we have for the stress in the stress and strain. So, the product of those two will give us the potential energy. So, this is per unit length over the area we have already integrated, and in addition to this term we have the potential energy because of the shearing of the element, which reads this, and these are all per unit length over the area we have already integrated. So, this times the small length and integrated over the length of the beam. So, that is the energy the potential energy expression. Now, this theta we have expressed theta in terms of our field variables W and psi. So, this is our potential energy expression in terms of W and psi, and this is the kinetic energy in terms of W and psi. Now, we apply the Hamilton's principle. Which says so, the variation of the kinetic minus the potential, this must vanish. So, if you take this variation, So, this is the variation of this kinetic energy, translational kinetic energy. So, this must vanish. Now, we want to take out this variation delta W out common from here. So, in order to do that, we have to integrate this by parts with respect to time and this by parts again with respect to time, and I mean these steps we have discussed many times before. So, those terms at T 1 and T 2 must vanish. Now, these terms we have to for example, this term and this term we have to integrate by parts with respect to space. So, when we do that, so because of this term we have this, and so these are the boundary terms. So, this term gets differentiated with respect to x. So, this must vanish. Now, again using the condition of vanishing of these variations at the boundary and variation over the domain, we can again invoke the same arguments and obtain the equation of motion. So, we have to collect terms of delta W. So, from here the coefficients of delta W So, we can say that for arbitrary variation W, if this integral has to vanish, then this must be 0. Similarly, the coefficient of delta psi So, these are the two equations of motion that we have obtained before as well. Now, from here we now look at the boundary conditions. So, let us look at the boundary conditions which we obtained from these boundary terms. Now, we have two field variables, and corresponding to these two we have the. So, for example, for this so this equal to 0 or psi. So, these are connected by or, they are conjugates. So, this is the angle and this is the bending moment, and at L so these are the possible boundary conditions obtained from here, and from here and similarly at x equal to L. So, these are the possible boundary conditions that we have that we can usually have. There are other possibilities. Now, as we have seen before as well. So, this set of boundary conditions, these are the geometric, while this set, these are the natural boundary conditions. So, these are conditions on the bending moment or the shear force, etc., and these are on the boundary, the angle, the rotation or the transverse deflection, and these are conjugate these are one is the conjugate of the other. So, this is the deflection is a conjugate of the shear force. Similarly, this angle, rotation angle, is conjugate of the bending moment. So, they come in OR, and so these are the possible boundary conditions we have. Now, this Timoshenko beam is still has it makes an assumption that the cross section which was plane before deflection, that remains plane, though it need not remain perpendicular to the neutral fibers. So, so this is a kind of limitation of Timoshenko beam, but then you can very easily relax this by introducing more complex functions for your deflection field. So, let us review and see what can be done. So, in this figure I have shown this Euler-Bernoulli theory. So, what it says is that plane sections will remain plane as well as perpendicular to the neutral plane, neutral axis. So, this was perpendicular here and it still remains perpendicular. In the Timoshenko theory, this was this plane section still remains plane, but now it need not be perpendicular to the neutral axis. Now, you can then think of higher order theories in which plane section need not at all remain plane. So, there is warping of the cross section. So, if you want to introduce or want to have higher order theories for beam for the deflection of beams or vibration of beams, then you have to relax this flatness condition of the cross section. So, we introduce the warping of cross section. So, to do that, here you can see the kinematics of deformation can be written out in this way. So, where capital U is the deflection in the axial direction. So, it is being represented in terms of these functions psi 0, psi 1, psi 2 etcetera, and expanded in terms of this variable z, which is the location of this fiber from this point from the neutral axis. Similarly, this transverse deflection is also expanded as a series as powers of z, where you introduce these field variables W0, W1, W2. Now, here this psi 0 introduces the stretch of the middle plane. So, using this kind of this deformation field, then you can write down the strains in terms of these fields. For example, the axial strain can be written as say del u del x, the shear strain can be written as 1/2 del u del z plus del w del x, and the strain in the z can be written as del w del z. Now, with these expressions of strain, you can write down the potential energy, for example, where this sigma xx, sigma xz and sigma zz are determined from the Hooke's law. So, once we have this, we can write down the potential energy. Similarly, kinetic energy can be written as 1/2 Now, once you have these expressions, then you follow the variational principle to derive the equation of motion. So, you can use this. So, by taking different kinds of expansion for the field for our field variable capital U and capital W, you can devise higher order theories for beams. So, what we have looked at in today's lecture, we have looked at the Timoshenko beam model, which uses the or introduces shear in the beam, which is, and this theory is valid for even thick beams, and we have briefly looked at how we can devise higher order beam theories. So, we conclude our lecture here.